Hello, my name is Cal Mazzola. I am a senior mechanical engineer and electrical engineering student, and my personal, I guess, oh my gosh,
Interest.
Personal interest in this project is sustainability. I am very big in sustainability. I think that renewable energy is the future of our world. It's how we do it, and this is an excellent kind of use case for it. It's a deep dive, and it was super interesting kind of figuring out how turbines influence our power generation.
My name is Colton Brown. I am a senior mechanical engineer, and my personal interest in this is the same as any other engineer as far as problem solving and learning something new. I am not as well versed in electrical topics or aerodynamic topics as some others are, and I found it very fascinating and fulfilling to have a project focused on those topics.
All right, my name is Ethan Shaw. I am a senior mechanical engineer. I work at GM, and my true passion for this project comes from my love for going outdoors. And in just less than a week, I'm going up to Canada, where the campground we're staying at is powered entirely off of wind energy.
Wow.
So that stems the roots of my passion for this project.
Excellent. So our presentation here is on turbine efficiency. Oh. Wait, you're going on now. Okay, that's fine. All right, so our path. How did we solve our problem? Well, we felt that we needed an experiment outline. What are we experimenting? What do we need to consider when designing a turbine? How are we going to produce electricity, etc.? We went into our design considerations. What is our design going to look like? We thought it would be best to model it off a real turbine. Obviously, we decided 3 blades, as it's what most are look like. We went into creation methods. How are we actually going to create our turbine? Are we going to 3D print it? Are we going to shape it from wood? Are we going to use a laser cutter? What are we going to do for it? Our experiment setup. How will we collect our data? What is the setup for this experiment? Where are we going to do it? We felt that the wind tunnel here at Canada University would be best. LED illumination. We had the bright idea from Dr. Berry himself to illuminate an LED. Let's showcase the actual power our turbine can generate and how that relates to almost the electrical grid that the United States uses. Voltage, current, resistance, and power data. I am an electrical engineer. I thought it would be great to combine fluid mechanics with electrical engineering and look at our voltage, current, resistance, and power data and how this relates from real turbines producing energy for the power grid. Power efficiency calculations. How did we get our power efficiency numbers with our voltage, our current, what's the difference between our wind speeds, etc. here. Turbine efficiency data. Now that we had a real wattage output from our turbine, we can correlate this with real turbines that the real world uses, right? How efficient is our design? What can we improve? How can we change it, etc. Finally, we included all of our data, our learnings, our environmental impact, etc. This is 30 slides, and you can see some images here of our turbine in the wind tunnel. We have a kind of a front-facing view and a top-facing view here. That's how we tested it.
Okay.
Our experiment outline. First, every good experiment needs a hypothesis. How does the shape of a turbine blade affect its ability to capture energy from a streamline and produce power? We knew that we needed to model and print 4 different blade designs. We felt that this would be a reasonable sample size to test in our experiment. We're going to test the blades in the ESL wind tunnel. We're going to collect power consumption data to get our voltage, to get our current, our LED illumination, the pressure differential, our energy transfer from the airstream to our turbine, as well as and measured against wind velocity. We're going to be testing at different wind velocities. That's going to get us how our turbines themselves can harness energy from the airstream. And then we're going to analyze and report the data. Here you can see a Fusion 360 CAD render of one of our turbine blades, and here is the printer we used.
So, in the design process of our turbine, we wanted to make sure that we were getting good data for it, and we had to consider the boundary layer. Even though the wind tunnel is very smooth, we were under the assumption that just like anywhere in the real world, as fluid goes across the surface, air will stick and drag to it as it has viscosity. And we wanted to ensure that in the center of the air tunnel where the wind is moving the most consistently, that's where our turbine would be collecting the wind. Similar to real turbines, how they are elevated off the ground, and the boundary effect is mitigated for them. So here's just a cross-sectional view of the wind tunnel, where the wind turbine is about 10 inches tall in a 18-inch square wind tunnel. The blades, just like in real life, are located at the front of the wind stream. So as the air approaches, the first thing it hits are the blades. We want to do that to minimize exposure to turbulent air and to make sure that it's getting the regular wind with no extra influence. Yeah.
So for some of the blade design methodology, the key concept here was making these blades able to capture the energy from the wind and convert it to a rotational energy, which would then be used with a DC motor acting as a generator to make electrical energy. So what we wanted to do was limit the turbulent flow over the blades, and how we did this was by smoothing out around the edges to make sure that the designs didn't have any blunt or flat ends on the leading edge or the tailing edge, and also limit the angular momentum by trying to bring the center of mass of the blades closer to the axis of rotation. And this would therefore make the blades easier to spin up as the wind velocity increased. And then also one of the key concepts was to make these designs 3D printable. So here's a example of a blade that was fresh off the printer. As you can see, there's lots of support on the underside, and this support gets peeled off. And 3D printing is really great. It's one of the most versatile design methods and manufacturing methods, but some of the issues with it are, at this scale, we weren't able to accurately depict what an exact turbine blade looks like due to the small leading and tailing edges on an actual turbine. So I'll pass around a couple of our blades as I talk about them. But you can go to the next slide. So here's a cross-sectional view of our blade versus an actual production wind turbine blade. And as I was saying, with these small points and angles, those would easily break at this scale for 3D printing. So we had to simplify this concept to ensure we were getting repeatability with our manufacturing, as well as simplicity for the design and changing slight things to the design. So go to the next slide. So here are our 4 different blades. We're looking at the cross sections of them. So for 2 of our blades, we had 20 millimeter cross-sectional width of the blade. The first blade was at a 30-degree angle, and the second blade was at a 15-degree angle. For blades 3 and 4, we had a 10 millimeter blade width with, again, that 15 and 30-degree blade angle. So as far as the methodology goes of the design, we needed to incorporate multiple components to create a working turbine. So the first thing that we needed to consider was to use a DC motor to act as a generator. So in taking Mech 311, which is mechatronics, we used the Arduinos. And this DC motor actually comes from that Arduino kit that we purchased for Mech 311. But we needed to consider a windmill that would be sized appropriately for the tunnel. So this was, like Colton said, around 10 inches tall, and the wind tunnel is 18 by 18 inches. And another design factor was making these blades easily interchangeable. So what we did to accommodate for this was make a square piece that each of the blades could slide onto to fit snug and allow quick changes while we were testing. The other thing was to reduce our turbulent flow. So our DC motor was actually housed in this piece right here. As you can see, the tailing edge is rather streamlined to reduce turbulence coming off of the back of the motor. Another concept that we found important was to hide the wiring. So the wiring for this DC motor actually runs through this pipe and out the bottom of the tunnels to reduce, again, drag or turbulence that would have been created. And this also prevents damage to the wiring. can go. So like I just said, the turbine head was important to reduce the drag. Also the base, we wanted to reduce any turbulence there, so it was rather streamlined and smooth to the bottom of the wind tunnel with a flush surface that we could easily tape down. So for the design methods, or for the, obviously I covered, we designed 4 different blades using Fusion 360. We printed them out and then assembled these in a fixture with an LED.
Got it. Right.
So for the materials used for this experiment, like Ethan said, the DC motor was something we had already purchased for another class. 10-inch length of half-inch PVC pipe is also very affordable. Filament, only 200 grams, is not too bad. We were in possession of a personal 3D printer, which helped us better control the variables. If not, we would have been able to use one at the school. Multimeters, we're all very hands-on people, so we all had multimeters available to supply for it, and then LED diode from the kit, and wind tunnel afforded to us by attending this university. The total out-of-pocket cost for all of the expendable items was less than $10. So this was a very affordable way to run an experiment with a series of designs.
So for our experiment setup, we contacted Ray Russ to help us with the wind tunnel setup. He provided us an acrylic base with an opening at the bottom for our wires. You can see here we tried to mount our fixture at the centermost point within the wind tunnel. This is to get the optimal streamline right in the center of our area. We had it taped down to minimize any turbulence here. We kind of tried to tape over any rough kind of edges in the sides and the bottoms. And we had our cables nice and even running through a hole in the back. You can see here with the blades off, in seconds we could interchange blades. It was super wonderful.
Okay.
So here we can actually have a video of the blades spinning.
So that was the most efficient blade running at 30 miles an hour. For each blade, we made sure to approach it slowly, just in case there was any unbalance in our blades, but they all performed very well. So we were able to get data up to 50 miles an hour for each.
Whoa. Oh, no. There we go. All right, so here's a video of our blade illuminations at blade 3 at 20 miles per hour. We chose this video because it showcases the LED getting voltage, however, a very low amount. We found blade 3 to be one of our less performing blades.
Okay.
Let me see here. So the diode is flickering.
Yes.
Yep, so you can just barely see that. And that's just indicating a very low
Right.
voltage. It's getting some, but it's not. The
Right.
DC power is not quite enough. That's what resulted in our flickering effect, and we measured our voltage and current over this LED. Here, you can see our blade 2, which was our highest performing blade, and we recorded the illumination and power at 5 different miles per hour. However, these were our 3 most illuminated. You can see here at 30 miles per hour, it's just slightly illuminated at 0.3 watts. 40 miles per hour, much more illuminated at 0.45, and our maximum wattage we achieved, which was almost 0.7 for the 50 miles per hour blade 2. You can really see it illuminate here. So this was blade 2 at all of its illumination. At 0, it was at,
All of the different
This is
blades.
every blade at 50 miles per hour.
Right.
So you can see blade 1 here at 50 miles per hour performed 0.3 watts. Blade 2, its maximum at 0.7. Blade 3 at 0.4, and blade 4 at 0.2. So blade 4 was actually our lowest performer at 50 miles per hour. Voltage versus wind speed. So we calculated our voltage, or we found and plotted our voltage versus wind speed. We converted our fan hertz to miles per hour as well as meters per second. However, for the sake of this, we used miles per hour as more discrete intervals. For blade 1, you can see they all have a positive relationship. However, some are much greater than others. You can see here blade 2 performed the best, whereas blade 4 performed the worst. We also plotted our current, and thanks to electronics, in electricity, voltage and current have a linear relationship to each other. So we would expect very similar graphs here, and that's exactly what we got. We actually drew the circuit out here, and which we'll go into in the next slide, but current measured in amps, measured using the breadboard LED setup as shown right below here, and we had our voltmeter just on both sides of the diode. And I made this little diagram. We have our voltage source, which is the turbine, which with some amount of resistance, which we were able to calculate thanks to having voltage and current in the diode. So next slide here, we give our resistance calculations. Resistance is found with Ohm's law, V equals IR. Resistance in any circuit is inevitable. You cannot escape it. But thanks to having our calculations, we found that for blade 2 at 50 miles per hour, which is our highest power production, we found our voltage to be about 3.77 volts with about 0.1 amps, and that got us about 21 ohms of resistance, which is a pretty low amount. You can get resistors that size. I would say it's quite proportional for the circuit, maybe a little higher, but not too bad. It was really interesting to see this, and this would be a very similar resistance throughout all of our blades because it scales linearly.
And then for power, you multiply the voltage and the current to find power, and as such, since both voltage and current were increasing, the rate of power as both of those increased was quadratic.
Okay.
And yeah, as using a DC motor, it was brushed. It's a brush motor, and it turned the rotational energy into electrical energy. So here you can see that effect I mentioned, where each of the graphs tends to have a little bit of a curve as the wind speed goes up. So for the turbine efficiency calculations, we had a few things we needed to get first. We needed the mass flow rate of the air moving in the cross section of the turbine. And then we also needed the recorded and calculated energy or power generated by the turbine itself while it was at that speed. And we need to, like I said, calculate the wind energy using the energy equations provided to us in fluids. So here are graphs for all of those effects. When we plot the energy retrieved by the turbine and the over the energy within the streamline, we see graphs where the efficiency, the highest efficiency we got was around 2%, and you can see the efficiency go down as the wind speed goes up. This is partially due to a result of the energy within the streamline increasing at a cubic rate compared to the energy retrieved. And here we used all of the setups, the formulas and equations we had found to apply the same principles to data of a real wind turbine. So this turbine had 12 meter long blades instead of 100 millimeter long, and that was taken from Penn State College. And here we found that the actual turbine was able to retrieve over 40% at 10 miles an hour of its wind energy and convert it into electrical energy, which is a very impressive number I was not expecting. And as the wind speed goes up, it falls as ours did.
Right.
So talking about the conventional wind turbine efficiency, in the example from Penn State, you can see just the raw data that we used to make these calculations. But looking at the power output of these turbines is insane. I mean, at 10 miles an hour, this realistic wind turbine is making 7,200 watts or 7.2 kilowatts of power. So this is how we used our energy equation to run the efficiency, was calculating the energy from the wind within that 12 meter radius cross section, and then taking the data from their power generation to get our efficiency values.
Okay.
So the conclusions that we took from this project, the question we had asked is, how does the shape of a turbine blade affect its ability to capture energy from a streamline to produce power? We found that with our setup on this small scale, wider blades generally proved much better at taking the wind power, and the shallower rake was also much more beneficial. It's similar to a sailboat sailing with the wind. The closer it gets to normal of the wind, the faster it can travel.
Okay, right.
As long as it can absorb that force. And yeah, the greatest efficiencies we saw were at low speed, where generating any amount of power with the wind at a quadratic function would yield a better efficiency.
Okay.
Yep, and some of our learnings. We have some charts here from energy.gov that showcase how engineers have developed their, practice of creating wind turbines throughout the years. We found that higher wind speeds yield greater wind and turbine power, but density plays a major factor for that cubic mass flow rate of air. But we also found many sources of loss. We found that a rough blade surface from our print can definitely increase the drag on our blades. A brush motor is not nearly the most efficient. A brushless motor would have been much better.
Right.
That brush itself creates a lot of drag within the motor itself. Small scale emphasizes friction forces, as we know. A much larger diameter blade would negate these friction forces better than what we are. Over the course of years, you can see a trend, this is published by energy.gov, of rotor diameter and hub height have been continually increasing as we further streamline our manufacturing, our transportation of these wind turbines. And hub height is almost a natural factor of rotor diameter, since the rotor is getting larger and need to get off the ground, right? We also found the environmental impact. Turbines as a sustainable energy source have grown exponentially in the past 40 years. It's actually been incredible to see how much they contribute to our power, to the United States power grid. As of 2022, they were producing almost 450 billion kilowatt hours worth of energy for our grid. That is absolutely astronomical. In 20 years alone, that has gone up by 400 billion. That's absurd, and it's a testament to the true power of wind turbines for our renewable energy grid. And as we said, high density air is desired. The lower you are, the better. You can operate more efficient at slow speeds. That's why we see so many wonderful offshore wind turbines. Oceans are an ideal place for this. Grasslands are an ideal place for this. Blade length and hub heights increasing, as we saw in the past slide. And like I said, this is 10% of all energy generated in the U.S. is because of wind turbines, and that has absolutely grown exponentially. So.
Okay.
That's all
Wow.
we have.
Okay. Any questions?
I have a
Question?
question. Is there like a limit speed or voltage that you guys ever tested from the project, or was it just the speeds that you guys wanted to test?
So we were afraid that at the high speeds and the angular velocity of these blades, we were afraid that since they were 3D printed, they would basically disintegrate and become shrapnel going through the windmill. So we were hesitant in our testing. We actually, the first blade that we reached the 50 mile an hour velocity point with was our least efficient blade, because we knew that the power generated by the blade was a direct correlation with the velocity of the blades. So, yeah, go
Well, one
ahead.
of the other reasons we went to 50 miles an hour specifically is because that's where a lot of wind turbines are designed to operate in. So we wanted to reach an equivalent speed for that indicator. But other than that, we just didn't want to push it too far. We thought we had a good amount of data from the 5 points.
Yeah.